Hello, welcome. Today I'm going to be talking about something called the normal mixture distribution. Now, this distribution is used in domains like finance, clustering, and machine learning. So I'm going to be giving a quick discussion about this particular topic. We always start off with something that we want to compare a distribution to. Now, we know about the normal distribution. Okay, so where there is a mean and a symmetric tails. Okay, now this distribution is useful in things like age, height, things that are fixed. If we're to explore outcomes in other domains, for example, in finance, this might not capture the actual dynamics that occur. Okay, so for example, if there's a two market regimes, one could be very calm and one could be very volatile. Okay, so we use something in those kind of cases, we use something called the Gaussian mixture. Okay, and here's a little bit of a brief mathematical overview. Okay, so we've got this summation, we've got number of components. Okay, where we combine two normal multivariate distributions, right? The pi k are basically the weights, okay, and they have to sum to one, right? And these are the multivariates. We saw this in a earlier YouTube video about the normal distribution, so I'm not going to go deeply into that. We do need to calculate log probabilities, okay? So we have to take the log of this term. And the reason why is because we want numerical stability. Okay, so that's basically what the mathematics here briefly explains. Now, going into like a real example, okay, we talk about the Gaussian mixture, and I create two um, multivariate normal distributions with two different means, zero point 0.01 and the scaled standard deviation is 0.075. Here, negative 0.65, and then 0.15. So you could see that the standard deviation is a lot larger for the returns on the second one. And you could see also that the mean is a lot lower. We've got like a negative mean here, okay? Now, if you look at this, basically you could kind of see one distribution where it's pretty much stable and then another distribution, okay, that has like negative outcomes. This is something that that reflects pretty accurately how stock market returns can behave. Okay, you can have periods of calm where it's bounded, right? You're not going to lose too much, and you're not going to win too much. But then there are outcomes. There are regimes or parts of the stock market returns that it could be the returns could be extremely volatile, where you could lose all of your uh, stock market value returns, right? So it's this is what the Gaussian mixture is actually useful for. It's saying, hey, look, we're not always going to be in the symmetric type of regime, right, where the outcomes are pretty much well defined. Okay. So if we use this GMM dot score samples from this Gaussian mixture scikit-learn function, we could calculate the log probabilities. Okay, and then we could reconvert that to the PDF by taking the exponent of the logs. Okay, and this is what this does: is it basically calculates the Gaussian mixture density. Okay, so this is not normal. This would be called a normal mixture. In terms of terminology, people think, okay, it's still a normal. No, you would not consider it normal at this point. You consider it a normal mixture. Now, here's another example of a normal mixture. Here we've got a negative mean and then a positive mean. Okay, so we could see that this one has a negative mean, and then here, if we look at it, approximately falls down to being positive. Okay, but they share some some aspects of their distribution. Okay. Now this is bimodal. What if we wanted it? There are cases where it could be unimodal. Okay. And I'm going to show you right now. So here we've got a unimodal distribution. Like we've got different standard deviations, so you could see that it's reflected in this. Okay. It goes to -4, and this really doesn't go that much. It goes maybe to 5. Okay. So you could see that like different standard deviations could influence how the diagram looks and of course, different means. Again, maybe if I make it a little bit larger. So yeah, I mean, you could see this where it's like there's a lot of more unlikely events that are going to occur. Okay. And it doesn't even recognize the density that well. So let's try another one. What if I did that 1, -2? Here it goes back to bimodal. So those are the different types of components, if you will, that could kind of occur under a Gaussian mixture. You could have a bimodal, unimodal. You could have more than that as well. You could have 3 or 4 modes. Here we're simplifying the example just to make it interpretable. Here's a Gaussian mixture implementation. Okay. Here we extract the parameters, okay, from this implementation. Now, underneath the hood is a EM algorithm, okay? And if we look at this, basically we're calculating the log probabilities, we're taking the PDF total, and we get the combined GMM total, okay, the dashed line, where the orange and the blue are the densities for component 1 and component 2, okay? So we're using something called an EM algorithm. Look, before I talk about the EM algorithm, we look at the weights from the GMM Gaussian mixture, and we could see that they're roughly equal. And, this is reflected in the graph as well. Okay. It's 0.504, 0.49. It's not that big of a difference. Okay. Now we use the EM algorithm to optimize for these parameters, right? Like how much weight should a specific distribution be given based on the data? What's the optimized mean and what's the optimized standard deviation? Now recall that the standard deviations are found in the covariance matrix on the diagonals, right? The variances are, so we take the square root. Now, how was this found, the EM algorithm? Basically, we initialize the values, mu, the covariance matrix, and the weights. We calculate the responsibilities. Okay, so how much, what soft assignment, it's a soft assignment, basically, what a responsibility is. And that point could belong to multiple clusters, right? So it's a soft assignment. It's not like k-means where you are definitely given one cluster or the other. So this is a little bit more flexible, the Gaussian mixture. The M step updates each of these parameters, and basically there's some type of convergence criteria, and it stops when the log likelihood improves less than a specified threshold of the maximum number of iterations reached. Okay, so that's a brief description of what the EM algorithm is doing behind the scenes in this GMM function. Okay. I'm not going to go too deep into the EM algorithm. I think I'll be giving that in another video. But here's basically this was basically a quick overview. Now, there's also something called AIC and BIC, okay? And this is basically the goodness of fit. it's balancing between the goodness of it and the model complexity, okay? And we basically see at this global minimum is the optimal value. Now, this is important in our next example when we try to model Microsoft, okay, returns. And just to give you a quick overview of the code, I basically download Microsoft, I calculate its returns, I drop the values and reshape it for the mixture model. As we all know that we have to reshape it to have scikit-learn take that particular formatted value. And then we basically try to come up with what's the optimal number of components. Okay, so before we saw 2. In this case, it's going to end up being 2. But we calculate the AIC and BIC scores. Whatever minimizes it, right, will be the optimal components. So we plot the AIC, BIC scores. We choose the number of components with the lowest AIC, BIC score. We fit it, the GMM against the returns, and then we basically predict the regime for each observation, and then we visualize the regime. Now here we could see that the plot, the BIC is at a minimum at 2. So when the BIC is at a minimum at 2, okay, that's the number of components that GMM has picked up, Gaussian Mixture Model. And now we could see the regimes here. Here we could see that there are 2 regimes, right? One bull market, here's one bull market and another bull market, okay? So we'll count that as like one regime. You could count it as 2 because technically you could count it as 2 because it might have different mean returns. Like here it looks like it's more pronounced, the increase, and it would have higher mean returns for this regime. But for simplicity's sake, we're going to keep it at 2, okay? I could go back and then try 3 components here, like in the actual algorithm, right? Where I just put this at 3, but I'm not going to do that. I let the AIC, BIC choose, okay? So there are times when you get results and you're going to want to dispute it and try other things, okay? But on a one run, in your first run or trying to optimize for the model, it's best to just look at the AIC, BIC scores and look at it at face value and trust it straight out. So in this case, we could say we have two market regimes. We have 2 bull markets, right? We'll count that as 1, and then a bear market regime. Okay, so based on that, we could say, okay, yeah, there are two regimes. We saw that basically this was for approximately 5 years. We saw it was going from 2020 to 2025, okay? But say if we wanted to look at a longer time frame from 2010 to 2023, we could also run something like this, the BIC score, and we'll find that this time the number of components is 4. Now, this would match up with our intuition, right? Because the longer you say hold on to a stock, I mean, in this case, 13 years, the probability that if it having a switch between bear market and bull market, it's probably going to be greater, right? There's probably going to be more things that happen also in between. So this is the kind of the end of our discussion. You could see that the Gaussian mixture has a lot of applications, especially in quantitative finance. It's extremely helpful. Other applications are like, say, housing prices in 2 vastly different neighborhoods with respect to income could be another example. So thank you very much. I hope you enjoyed the video, and hopefully I'll see you in the next one.